So these are the main concerns that we have when we have these eruptions from the sun. They may actually either disable our satellites, so we have to reboot them, or they may actually completely damage the electronics on board.
Hello, everyone. I'm Colleen Stover with the Aerospace Corporation, and this is the Space Policy Show. Today, we're talking about space weather, what it is, how it affects our satellites and satellite services, and what we can do to protect against that. We've got on Paul O'Brien, Senior Scientist at the Aerospace Corporation, and Juha-Pekka Luntama, Head of Space Weather Office at the European Space Agency. Thank you both for joining.
Thank you, Colleen.
Hi, Colleen. It's great to be here.
Great. So, Paul, let me start with you. Can you just give us, a short intro of your background? Why did I want you on the show today?
Yeah, I'm a research scientist at the Aerospace Corporation. I've been doing this about 20 years, and my specialty is in satellite anomalies, satellite design, and the radiation environments that cause concerns for those things.
Thank you. And Jussi, how did you get to the position you're at?
Well, I joined ESA about 15 years ago as the head of what was called the Space Weather segment. At that point, it was part of the ESA Space Situational Awareness Program. And then when the program grew into what we currently call a Space Safety Program, I became the head of the Space Weather Office. So I'm responsible for developing the Space Weather System for ESA and also actually the Space Weather capability for Europe.
Okay, wonderful. So, and we are here to talk about space safety. We're starting off with the big one here. So, Paul, let's jump in. For our audience, what is space weather anyway? What's the difference between one of these kind of feared solar maximums and other large particle events?
So, space weather is an ongoing day-to-day, almost meteorological phenomenon. It goes on, of course, in space, but it starts at the top of the Earth's atmosphere, extends all the way to the surface of the sun and to some degree inside the sun. And we will talk a little bit about plasmas and radiation. Those are particles that are, normally we interact with neutral particles, atoms, molecules, those sorts of things. A plasma is so energetic that the electrons that would normally be attached to the nucleus have been stripped off. And so you have separate nuclei and electrons, and it's a kind of a electromagnetically charged soup. And it starts at the sun, it flows through interplanetary space, it interacts with the Earth's magnetic field, and then it reaches the top of the atmosphere. And in doing all of those things, it can cause a variety of concerns for human activities.
Okay, so our electromagnetic soup, how long does it take to get from the sun to Earth?
Usually a few days. The speed of the primary set of particles that come from the sun to the Earth are called the solar wind, and it usually takes a few days. When the solar wind has a major eruption from the surface of the sun called a coronal mass ejection, that can get here within a matter of hours, and that is a major concern for a variety of operational activities in and near the Earth. And these things happen all throughout the solar cycle. You mentioned the solar max that's coming up, which is certainly a concern. The certain phenomena are more frequent at solar maximum. Other phenomena are more frequent in the rising and declining phase. And that maximum refers to the number of sunspots visible on the surface of the sun. And so there's more activity typically when there are more sunspots.
Okay. There's differences, though, isn't there? There's like these geomagnetic there's solar wind versus corona flares, and they all kind of create these different phenomena, right?
Yes. There's typically solar wind is present all the time, and it can cause interactions at the Earth that can be day to day, even when there's no eruptions or flares going on. But a lot of the attention is focused on these eruptions, these coronal mass ejections, which are often accompanied by a flare. And there can also be solar radio signals that we call solar radio bursts, which can cause interference. And so you begin with this eruption at the sun, which ejects a lot of energetic plasma into space and also creates the flare, which is a photon phenomenon. So photons are light particles as opposed to massive and charged particles. That all reaches, the light reaches the Earth within 8 minutes, speed of light. The plasma reaches here within hours to days, and it causes storming in the Earth's magnetic field, which we will call a geomagnetic storm. And then it can also cause storming in the ionosphere, which we may observe as aurora. And that's one of the most well-known features of space weather is the visible aurora that you can see with the naked eye if you're up at night in a dark, cold, dark place.
Yeah, yeah. That's the good part, right? The pretty lights.
Very much so.
So you see, what can you add to this? I know that maybe start off with some history of some of these phenomena, like the Carrington event. That was a really pretty aurora light.
Yeah, you could say that. And actually, it was where no aurora has ever been seen before. So basically, people admired aurora in the Caribbean islands during those times. So basically, that was the biggest space weather event that we know of. There have been bigger ones in 1859.
Okay.
Yeah, it's there have been bigger events in the history. We know that from some tree stump samples and ice core samples, but that's the biggest that we know of with the real observations. And yes, I mean, that was the event that disrupted the high technology of that time, which was the telegraph lines. So basically, the telegraph lines became red hot, and they started fires in the telegram offices. So that was the power of the solar event in 1859.
Wow. Well, so you've touched on, I actually was reading recently about that event, and telegraph operators were able to still send messages without, like, they were disconnected from the battery because it was charged for so long. So
yeah, and you could actually claim that that was the first use of solar power in telecommunication.
I like it. I like it. What other, so, you started with that one, but what other impacts of solar weather can you talk about, you see? What's the science behind these kind of solar storms and how they create problems for satellites around Earth?
Well, I mean, for the satellites, it's this plasma that Paul just mentioned. It's these charged particles. They are the biggest problem. As Paul mentioned, we have constantly the solar wind impacting the Earth. And the environment in space around the Earth. But what can happen actually is that when we have these eruptions in the sun, the coronal mass ejections that Paul also mentioned, sometimes these particles get accelerated, just like in a particle accelerators that we have on Earth. But this is a giant one around the sun. And these particles can actually reach speeds which are relativistic. So they can reach speeds up to the close to the speed of light. And these particles reach the Earth from the sun in the matter of 20-30 minutes. And if they impact satellites in space, they can seriously damage the electronics in the satellites, but also some slower particles, slightly slower plasma that we get sometimes from the sun, that can cause what we call surface charging. So basically, the surface of the satellite becomes charged to the charge of tens of thousands of volts. And then you can imagine that then if there is a discharge through the electronics of the satellite, so there's basically a lightning strike inside the satellite, that's not good for the electronics. So these are the main concerns that we have, that when we have these eruptions from the sun, they may actually either disable our satellites, so we have to reboot them, or they may actually completely damage the electronics on board.
Right, right. And there's also something about the atmosphere, or the part around the Earth heating up a little bit, right? So talk about that.
Yeah, there are two things. I mean, the energy, the particles from the sun, but also these photons that Paul mentioned, the solar flares. What they do is they impact the upper layers of the atmosphere, the part of the atmosphere that we typically call ionosphere, or the thermosphere just above it. And two things happen. One is that the atmosphere warms up there. It doesn't help us when we have a cold winter day on the Earth, but up there, the satellite warms up and it expands.
The atmosphere kind of warms up and expands, yeah?
It expands, and that impacts the orbits of the satellites. I think many people might remember an event 2 years ago where some satellites were lost because the atmosphere was thicker than expected, and the satellites actually couldn't reach their orbits. But the other thing that happens, which is also very important, is that this ionization of the upper atmosphere it disturbs satellite signals. And if we have a solar event, we have a strong solar flare. If you are in the daylight area at that time, you might actually notice that your mobile phone doesn't find your location anymore because the navigation satellite signals are actually blocked by this ionization of the upper atmosphere.
Okay, yeah. So, well, you've kind of gone into a little bit about, my thing is, all right, so some satellites are, they got a little lightning happening inside them. But satellites don't have mothers. It's not hurting anything, right? So what's the big deal? So Paul, let me start with you and then I'll go back to you, C. Why do we care? What are some of the impacts that this could have to us on Earth?
Yeah, well, obviously we are very dependent on space in many ways. We use it for communications, internet, cell phone, television signals. A lot of national security information passes through satellites. We use them for navigation. And so if you're using in the US, we refer to it as GPS, that could be disrupted. And the space environment they're designed to handle the space environment. And so they should operate through all weather. But the reality is that sometimes things go wrong. And it's kind of like having a leak in your roof. Your roof is supposed to handle all kinds of weather, but you do occasionally get leaks, and that can be very disruptive. It could be anywhere from a small nuisance to a major, catastrophe in your house. And satellites are the same way. And so the space weather really potentially impacts the availability of those satellites or their ability to transmit information down to the ground through the ionosphere.
Yeah, I mean, I'm thinking if our position, navigation, and timing satellites were interrupted and you're in an airplane, I mean, what do you think, Jussi?
Well, I mean, fortunately, the airlines have a lot of backup systems, so it would disturb the flight. The crew would be busy for a moment to check what happened, and that's why actually we want to actually be able to inform people that there is something going on, so that they are not surprised. Because if you are aboard a plane, the last thing that you want is that the crew is completely surprised by something that they did not expect. So airlines are basically okay, but it would be a huge disturbance for aviation in total, because in those conditions, no airport would actually let any flights to take off. So basically, the flights would be grounded. And we have a couple of examples where something like this has happened in a small scale, but fortunately, we haven't had a big event during our current era of aviation. But that would definitely be a bad day to travel anywhere. And also, there is one thing that you might need to take into account also, that these particles that Paul mentioned and are coming from the sun, they also slightly increase the level of background radiation when you're flying aboard an aircraft at high altitudes. So basically, during those events, you would get a tiny additional radiation dose. But people are very sensitive to that. Airlines are very sensitive to that. So actually, many airlines have instructions that during those conditions, they are not allowed to take off, just to protect the passengers and the crew from this additional radiation.
Interesting. Oh, I didn't realize that. So we don't want any passengers turning green on the flight.
Well, you would not turn green. It's a small dose, but I think you want to be careful. And actually, if you fly frequently and you would get enough of these small doses, gradually you would actually, develop an increased radiation dose, which you want to avoid anyway.
Yeah.
So that's a concern for the pilots and the crews, who, of course, do fly very frequently, much more so than for the passengers.
Yeah, very true. So what about the power grid? What might happen with the power grid? Jussi, I know you had been talking about that a little bit in our pre-conversation.
Yes, I mean, the power grid is actually, it's one of the parts of our infrastructure, in addition to of course, the satellites in space that can be impacted by space weather more or less directly. Most other impacts are through problems in communication or other things, but power grid actually, there is a phenomenon which is called geodynamically induced current, which usually the jargon is GIC, so geodynamically induced current. Basically means that from space, from these particle systems that we have in space around the Earth, power may be transmitted directly into the power grid, these big, long power lines that we have on Earth. And this additional power can seriously damage the transformers. And again, we are talking about the big transformers, the things that are the size of a house that you see on the roadside as part of the power grid. Those actually may be damaged. They may actually practically melt because of this additional power. And that would cause a blackout, definitely, and a blackout that takes a while to repair. And this is kind of a feared event, that we would have a major disruption in the power grid that would take weeks, months, even in some cases years to completely repair.
Wow. So yeah, some very real potential happenings if we don't protect against that, right? So let's go into, I'm going to start with you, Paul. I thought that satellites are kind of built to recover from anomalies. I thought that they could, how do we design to protect against this, or how have we not done it, and how should we be doing it?
Well, we have a pretty long history of very robust satellite designs. The vast majority of satellites live their entire life with space weather causing at most nuisances. Those nuisances can have economic impacts, but there tends to be a balance between the engineering mitigations that one might take, which is a lot of ground testing, adding metal onto the satellite to shield it from the radiation, building in redundancy. There's a balance between those efforts and then trying to diminish the impact of space weather down to as near zero as possible. It would take a lot more money to get it down to truly zero. So there's a certain amount of accepted risk that's carried in most satellites. What's been changing recently is this introduction of these mega constellations, or sometimes called proliferated architectures. And that's where, instead of having one or two or three or a dozen satellites, you're now talking about hundreds or thousands of satellites. And in that kind of a system, it's much more difficult to try to knock down the impacts of the space environment and other things to very, very low levels, but you make up for it by having lots and lots of satellites. So instead of each satellite having onboard redundancy in the form of extra hardware, extra circuit boards, extra computers, so many of the best practices that we've developed need to be adjusted and rethought to deal with these sort of low cost, more vulnerable, but mutually protecting architectures. So that's a big development that we're trying to deal with and trying to balance the risks and the costs in a very, very different way.
Right. So the resiliency of having multiple assets flying, right?
That's right.
If I may add to that, another thing actually that you would like to do, or would like to avoid doing, is that when there is an imminent probability of space weather or solar event, you don't want to carry out any sensitive operations with your satellites. So you don't want to, upload new software into your satellite, or you don't want to plan a maneuver where you use the thrusters of the satellites, because if you lose communication just when you have started the thrusters, you're definitely in trouble, because your satellite will be drifting without control after that. So this is another part of what we would like to do. We want to inform the people that, this is a bad day to operate your satellite system. Postpone it by 24 hours. And you probably will be fine.
Yeah, so it's a bad day, maybe to launch things into space as well as maneuver things that are already in space. So
that is true.
What about predicting these then? How do we know they're going to happen? UC, what do you have to say for that? I know that this is the prediction centers. This is the fun part, I think.
Yeah, it's tough. It's very tough. what we can do at the moment is to observe when things happen. So we have good satellite systems. We have excellent people who can observe the information that we get from these satellites. We have also ground-based observation systems for that. So we can monitor the sun, and as soon as we see any kind of eruption in the sun, we can basically give out the message that there is an imminent space weather impact on the Earth. So please take precaution, be prepared, and also be prepared to take corrective measures for the system that you operate to make a real forecast that there will be a big event tomorrow. That is a major scientific challenge at the moment. We have science missions, and I want to mention at this point, for example, the Parker Solar Probe, which is a NASA mission with international collaboration. We have from the European side, from the ESA side, we have the Solar Orbiter, which is also international collaboration, particularly between Europe and the US. And these are the missions that we hope that will help us to make these longer-term forecasts. But that's really a major challenge. But this is actually this is Paul's area of speciality. So I would like to give the floor to Paul.
Yeah, Paul. And before you dive into some of your intimate knowledge with it, can you just give our audience an idea of the landscape of prediction centers around the globe?
Well, most nations have some level of space weather prediction capability if they have a space presence or if they have a ground presence that is affected by space. So if you don't have satellites, but you have power systems that are potentially affected by space weather, you'll have at least some national capability. The United States operates one of the largest capabilities at the Space Weather Prediction Center. But there, as Jussi mentioned, there's capabilities in Europe. There are capabilities throughout Asia. There are some growing capabilities in Africa. And so it's really present all over the world because everyone is affected by space weather, at least to some degree. And then the size of your facility will be somewhat related to how much vulnerability you have to space. And so as you might imagine, the U.S. has quite a lot more vulnerability than other nations. And so we have a fairly leading role in that. When it comes to the actual forecasting and the kind of tools that we're using these days, there's kind of two different modes that are done. We have human forecasters who, as Jussi was describing, they will watch the sun, they will assess the structure of the sunspots, they will look for eruptions, they will try to determine where those eruptions are headed at the Earth and how long they might take to reach the Earth and whether they might be severe. There's a second set of forecasts that are more, we use the term empirical. They're derived from data, and they often use artificial intelligence or machine learning. And these kinds of forecasts will tend to be a phenomena much closer to the Earth. It's just extremely hard to predict those eruptions from the sun. So the forecast that we might see for the Earth might look over the next several hours or several days to see certain phenomena at the Earth, say in Earth's radiation belts or Earth's ionosphere, that could have impact on human systems. And those are, at present, many of those are developed based on looking at prior data and learning the patterns in the data, and then looking at current data to see if it's starting to look like any of those previously hazardous patterns. And so that's somewhat different than the sort of human forecaster approach, looking at images of the sun and watching out for eruptions.
Well, and I wonder how artificial intelligence is going to play into that, looking at the past to try to predict the future better.
We feel it will play a very significant role, especially in analyzing solar imagery. But some of our data sets go back, 50, 60, 70 years. So we do have a baseline of training data that we can use to build artificial intelligence and machine learning systems.
Yeah. And so, well, we're talking, I already pulled humans out of the loop there, but I want to put humans back in the loop, right? So I do want to talk, I want to ask about human space flight safety, but I also, Paul, talk about satellite operators. Like, how are they being trained to receive the data, interpret the data, and then act accordingly?
The satellite operator training is very bespoke at this point. That is, each individual institution, organization, agency does things their own way. We are just now starting to see the growth in the academic institutions of training programs and degree programs that would feed into that career path. But to a large degree, it's an on-the-job training type approach, and it's highly customized to the institution. So some institutions treat their satellites the way we might treat a piece of consumer electronics. If something goes wrong, we have a certain amount of switches we can flip, reset, reboot, and that's about the extent of how they operate the thing. In other cases, they operate it the way a scientist might operate a delicate experiment in their laboratory, where they could, if necessary, they can reprogram things, they can dramatically reconfigure things, and they will go down, they will trace any anomalous behavior down to its root cause. So there's a huge variety of training and sort of level of detail in satellite operations, at least as regards space weather.
Yeah. Are there places that operators could go for like best practices? Does ESA or NASA put anything out in terms of that?
It's fairly limited. There's not like sort of a single book that one would say, this is the book on how to become a satellite operator. A lot of that information is still rather piecemeal. There's clearly a need for it, but it has not, at least to my knowledge, there is not sort of a comprehensive textbook on satellite operations with regard to space weather. There are many space weather textbooks that touch on satellite operations, but I'm not aware of one that directly would be treated as a general purpose training guide for a satellite operator to deal with space weather. Can you think of anything?
Well, I mean, from our side, what we have started to do since a few years is that we actually provide training courses. So we actually typically go to the site of a satellite operator. We have done it in many of the bigger satellite operator sites in Europe. And we give them a 1 day or 2 day course on space weather and how to utilize the information which is available. So it's kind of a hands-on training on this is what it means when you see this kind of a message coming. Then we leave it, of course, to them to decide what they do. So we don't teach them satellite operations. We just teach them about what space weather is, and then we work together sometimes to try to define what it means for their operations. Is it a good day to work, to do something? Is it a bad day to do something? But actually, I mean, just as Paul said, if you're a satellite operator, your main job is to keep the satellite online. And if anything happens, your first task is to get it back online. You worry about the root cause of the discrepancy or the anomaly later. But your first thing is to get the satellite back online. Whether it was space weather or another glitch on your satellite, that's a secondary problem. You just want to get your satellite back, providing communications, satellite navigation, making money for your company, whatever is the purpose of the satellite.
Yeah, no, that's a good point. So you see, talk to us. I'm human spaceflight. We've got astronauts on the International Space Station. We're looking at other kind of space stations around, commercial stations around the Earth, stations around the Moon, eventually, kind of working, maybe living on the lunar surface. How does space weather, talk about that interaction between space weather and human spaceflight safety?
I will start by going back into those particles that we discussed before. I mean, the same particles that impact the satellites in space, they impact humans. So you don't want to be there when you are showered by the solar particles. At the moment, we're still operating within the magnetic field of the Earth. ISS is in a relatively low orbit around the Earth, and it's protected by this magnetic field that we have around the Earth. So it's a relatively safe environment. But this will change as soon as we go outside Earth's magnetosphere. When we go towards the moon, when we are orbiting the moon or we work on the moon's surface, we are fully exposed to these particles from the sun. And again, it makes a huge difference whether you are inside a space station where you are protected by this shell, the metallic shell of the space station. But when you are outside in a spacesuit or you are walking on the surface of the moon, you are more exposed. And the challenge is that getting back inside the space station, if you're doing a spacewalk, it takes hours actually. or if you are far away from your lunar outpost, which is protected against radiation, again, it takes time to get inside. So what you would like to have is an early warning that there is a potential solar event that could create hazardous radiation conditions, so that you can start your way back in before you are hit by this radiation. And we know these events in space, in an extreme case, they actually can be so hard that you would actually, as minimum, get radiation sickness. Theoretically, the solar radiation, the solar particles could even kill you if you are outside a shelter in space.
I'm sure I've seen a science fiction movie with this in it, where the people are, running to get in before something.
Yes.
And that's what you might see in the lunar outpost. If there is a sudden solar event, you would see people rushing inside. But I hope that actually with Paul and with all the other colleagues who are working on this, we actually can come up with a warning that comes on time, so that you can walk in quietly, peacefully, sit down and wait for the storm to be over before you go outside again.
Yeah, have a cup of coffee while you're waiting. Paul, do you want to comment on the human spaceflight safety aspects here?
Well, I think that Jussi really covered a lot of it and a lot of good detail. I think that something that is often forgotten in that conversation is that the human depends on the space vehicle that they're inside. And so when you are sitting there having a nice cup of coffee, you also need to make sure that the vehicle itself is not having any anomalies. And so it adds together the two problems that we have often dealt with separately, of keeping the human safe and keeping the vehicle functional. You certainly don't want to have a life support system or some other failure due to space radiation while you're taking shelter.
Yeah, absolutely.
Actually, I mean, maybe just to add to that, these same particles actually do impact the avionics of aircraft as well on the Earth. And we know that when our electronics gets denser and denser and smaller, this impact, it becomes more sensitive to these impacts. And that's another good reason why the airlines don't want to fly when there is potentially high level of radiation at the flight altitudes, because that would increase the probability that some of the avionics might be impacted by space weather.
Yeah, it's a very interesting intersection of the costs and the designs versus the benefits. You can make an aircraft that can handle the 40-year worst storm, but if you just need to ground things for a few hours or even a day, compared to having every single aircraft built with that high level of protection, this is the kind of thing that smart engineers worry about and trade all of the time, trying to balance that cost and risk to make sure the systems are safe, but that they don't overdo it and waste a lot of money flying shielding around or launching shielding into space.
Yeah, that's a good point. So just, the economic benefits of prediction, right? So if you can predict it, then you don't have to build every single one to be that resilient.
Right. It's very much like earthquake prediction. We can't predict earthquakes right now well enough to evacuate a building, but we can predict them in terms of where they're most likely to occur and how big they'll be over a certain time horizon. And so there's a very similar approach when we design satellites and other space systems. Even if we can't predict them, predict the specific issues, we can always have some understanding of how likely a large event is and design to an event of a sufficient size that we think our system will get through its whole design life without having any kinds of problems.
Yeah, actually, I mean, maybe just quickly adding to that. This is actually, you mentioned, Kathleen, at the beginning, the solar cycle and the solar maximum. Actually, our engineers are taking this into account. So when we design satellite systems, we take into account whether the satellite system is meant to fly and live through the solar maximum, when it's more likely to get space weather impacts, or if it's a short-term mission meant to just operate during the solar minimum, then we can actually make it a little bit more efficient, have slightly less shielding, and make it less expensive.
Yeah, I was just going to ask about that. It's a 12-year cycle, is that right?
It's roughly speaking 11-year cycle, but that's purely statistical. So actually each cycle is individual, but it's typically it ranges from 9 to 12 years, which is related to the behavior of the magnetic field of the sun.
And so that's kind of forecast to be next year or the year after. Is that right?
Well, the one thing of the solar cycle is that the solar maximum, you only know when it's over. So we expect that it will take place around this year, but we only we can really be certain that the solar maximum is over when we start to see the solar activity gradually getting decreased.
Okay, so satellites that might be launched today that have an expected 5-year lifespan should probably be planning for some sort of maximum event.
That's correct. But then going back to what Paul said before, these big solar eruptions like the Carrington event, they actually tend not to care about the solar cycle. They take place anytime, even during solar minimum. So you can never be completely sure that your mission will not encounter some serious space weather.
Well, you're making me feel less and less confident. We're about at time.
We're pretty good at this, Colleen.
Right, but
yes, we watch all those buts and exceptions, but the vast majority of the time, the space systems behave exactly as they're designed to do.
Exactly.
Okay, so we are at time. I do want to thank you both for being here. And Paul, I know you wanted to comment on something. I see you're wearing a colorful shirt. I know that there's like a long history of the space weather prediction from even the 1950s. So why are you wearing such a colorful shirt today?
So this shirt is a Hawaiian shirt of sorts, and it commemorates the recent passing of my colleague, Bern Blake, who has been one of the pioneers of space weather and space environment observation. He worked at the Aerospace Corporation for many, many decades and was a mentor to many of us and was a real enthusiastic instrumentalist. Throughout his career, he could be found far more often in the laboratory, tinkering with some electronic setup, trying out some new kind of detection technology, rather than being in his office, writing all of those wonderful results up for the journals and the other scientists to read about. So this is the way we commemorate Bern, is that he started the tradition of wearing Hawaiian shirts, and so I'm wearing one today to recognize that.
Thank you. So we'll dedicate this show to Bern.
That'd be wonderful.
Okay. Well, thank you very much, both of you, for participating in this discussion. I've really enjoyed it. So
thank you.
Thank you very much.
Yeah, I think space weather is it's a great way to kind of frame the overall space operations safety. It's something that humans and operators in space, we can't afford to ignore it. It's also something that's kind of universal, that goes across any national boundaries of spacefaring nations. So yeah, we're just mere Earthlings, and we just got to deal with what goes on with the sun. So if you'd like to learn more about the Center for Space Policy and Strategy Research, you can go to csps.aerospace.org. You can browse all of our research by topic. And of course, we have a long history of space policy shows that you can browse across all kinds of topics having to do with space strategy and policy. All the shows are available on YouTube or wherever you get your podcasts. Thank you to James Liggins, our technical director. And until next time, everyone, thanks for joining.